video, I'm going to walk you through the process of solving triangles that are not necessarily right triangles using trigonometry. Um, just because I know the context in which we've developed trigonometry so far has been for specifically right triangles. But what happens is we can start to apply trigonometry in terms of non-right triangles in one specific way and in some specific cases. And in one of those cases, we can utilize what's called the law of sines, that the proportion that compares the sine of an angle to the length of its opposite side should be equal for all angle side pairs in a particular triangle. And what I mean by that is that the sine of one of the angles over its side length, opposite side length, is equal to the sine of another angle over its opposite side length is equal to the sine of a third angle divided by its opposite side length. There's a proof that I'm going to very quickly walk you through, and then we'll do some examples in this video. Though the idea is that I am not expecting you to remember the proof. I am expecting you to know how to utilize the law of sines in some problems that I might give you. And so we'll do some examples. The way that the law of sines is proven is by starting with some information that's given to you in a particular triangle that you don't know its specific type, but I know from this vertex angle here, I can draw the altitude to the opposite side and say that that altitude has a length of h. If I know that that's the case, I can set up two right triangles within this non-right triangle. I'll outline one of them in blue and the other one in green, just so you see those right triangles. And just keep in mind that those are triangles that have been developed from this one non-right triangle. So that being the case, I can set up some trig functions that if I wanted to know for the blue triangle what the sine of angle C was, the sine of angle C, it's the opposite side, h, divided by the hypotenuse of that right triangle, h over b. If I wanted to, well, we'll step back for a second and say, let's do a similar thing with the green triangle. If I wanted to know what the sine of angle b is, then it is the opposite side, which happens to be h as well in that case. Sine of angle b is h over the hypotenuse for that right triangle, the green right triangle, h over c. In both of these, it seems like I have a similar ratio with that altitude length h being in the numerator of both of them. And I wonder if I can reorganize this statement sum to get something meaningful out of it. So let's just see if we can do something. In this case, on this blue ratio, if I multiply both sides by b, I get that h is equal to b times the sine of angle C. If in the green ratio, I multiply both sides by the measure of side length C, then I get C times sine of angle B is equal to h. And noting that that's the same h in both of these pieces, I know that it must be the case from there that h is equal to h. So I'll pull one expression of h from this equation and one expression of h from the other equation. That c times the sine of angle B is equal to b times the sine of angle C. And I have some interesting proportionality that in some way the opposite side multiplied by the angle B that it's opposite or that it's adjacent to is equal to a similar ratio with B and angle C. Now, where the law of sines is developed from is using some of those proportionality relationships in order to move forward from this equation. So, for instance, in that equation, I'll divide both sides by C. On the left side, that C in the numerator cancels, and I'm left with the sine of angle B is equal to B sine of angle C divided by the measure of side length C. And I can divide both sides by B, much like I did for C. Divide by B. I'll have to move over the equation sign a little bit just to fit it. Divide by B. And if I divide by B on both sides, the B in the numerator cancels and on the right side, and I just have a B in the denominator on the left side, that the sine of angle B divided by side length B is equal to the sine of angle C divided by the side length C. And that's just one piece of the law of sines. That's one piece. The other ratios are developed in a similar way, that I could just pick a different altitude and do the exact same thing that I did here, and what I'll end up getting is something like the sine of angle A is equal to the sine of the sine of angle A divided by side length A is equal to the sine of angle B divided by side length B. And since I know that that ratio is equal to the sine of angle A over A, and it's equal to the sine of angle C divided by C, they must all be equal to each other. That the law of sines holds true because of the ability to take a non-right triangle, draw in an altitude, and think of it as two right triangles put together to form that one triangle. Now that's just the general idea of the proof for you guys. The law of sines can be used in only one specific set of circumstances. And that set of circumstances is if in your given information you're given at least one angle side pair. An angle side pair. And when I say an angle side pair, that means that if I'm given one particular angle measure that I'm able to find the sine of, I have to also be at least given one opposite side for an angle measure that I'm given. Um, any other setups might have some other different opportunities, but in order to use the law of sines, I should think of I at least need one angle side pair. And what I mean when I say that is if I'm given the measure of angle A, I also need to be given A. Or if I'm given the measure of angle B, I need to at least be given B. Or if I'm given the measuring angle C, I need to be at least given side length C in order to solve using the law of sines. Let's do an example. Uh, there's some more work that's to be stated here, but I'll let you go through that on your own. In the first example, using the given information below, solve the triangle. And I'll remind you that solving the triangle means finding all of the angle measures and all of the side lengths. The angle measures are easy, right? Because in this case, I can use the triangle angle sum theorem to say that I know the sum of the angles in a triangle has to be 180. So if the measure of angle A is 59 degrees and the measure of angle B is 38 degrees, then it must be the case that the measure of angle C is equal to 180 minus 59 minus 38. If I pull out my handy dandy calculator, 180, 180 minus 59 minus 38, I get that that's equal to 83 degrees. So the measure of angle C is 83 degrees. Since this is a right triangle or a non-right triangle, I can't use the typical things that I would do to set up like a sine ratio because I'm not told it's a right triangle, but I can use the law of sines that the sine of an angle, in this case I'll say the sine of angle A divided by side length A is equal to the sine of angle B divided by side length B. That in order to use the law of sines, I need to be given at least one angle side pair. The rationale behind that is I need to be able to set up what the ratio equals for those two pieces of information in order to use it to solve for the values on the the values of the sine of angle B and the side length B. The law of sines would tell me that the sine of angle A, 59 degrees, divided by the side length A, 350, is equal to the sine of angle B, sine of 38 degrees, divided by B. And our goal is to solve for B in this case. In order to do that, we should always first isolate B on the side of an equation by itself. That I may need to do some cross multiplying and then dividing in order to isolate B, but that's the overarching goal. So let's do that. Let's use the means extremes property to cross multiply. Um, B times the sine of 59 degrees is equal to 350 sine of 38. And then lastly, divide both sides by the sine of 59 because the goal is to get B on the side by itself. Divide by sine of 59. And the exact value of B is 350 sine of 38 divided by sine of 59. Now I can stick that into the calculator. If I do, I get 350. Oh, and also make sure that when you're using your calculator, I guess I forget to say this often, but make sure that your calculator is in degree mode and not radian mode. Degree mode, the DEG, and not the RAD. We don't want radian modes just because we are not dealing with radians in this class. That's for next year and the year after for you guys. So let's proceed forward. 350 times the sine of, where's the sine button? Oh, here it is. Sine of 38 divided by the sine of 59. And when I enter that into my calculator, I get that B is equal to 251.388. And we're going to stick with that convention of rounding to 3 decimal places for side lengths, 388. Now I just need to find one more additional piece of information. What is the side length C? And much like I did for B, I can set up the law of sines in order to solve that. What you might notice is that these problems are fairly long and that they require a bunch of intricate information, but I don't think the process is difficult. It's just a matter of setting it up appropriately. So from there, the sine of course, that side that we have the angle side pair for, 59 over 350 is equal to the sine of 83 degrees divided by C. And from there, we would cross multiply as well, much like we did in the other problem, or the other part of the problem. C times sine 59 is equal to 350 sine 83. And then lastly, divide both sides by the sine of 59. C is equal to 350 sine 83 divided by the sine of 59. And when I stick that into my handy dandy calculator, I get sine 83. I get that is 405.278. 405.278. I guess I should include the centimeters just because it was included in the original problem. But generally speaking, that's just how you would use the law of sines, that you set up the appropriate values and you set up the appropriate ratios using the statement of the law of sines. And then from there, you cross multiply in order to solve for what you need to. In this problem, it wasn't so bad insofar as finding the angles were fairly easy. It's not always the case that it's going to be as simple as that because it gets a little more intricate in the case of using the law of sines where you're only given one angle measure and you might need to solve for other angle measures. So in the second example, that's what we're going to end up doing, that we're given two side lengths and an angle measure, and we need to find the other angle measures. Just reminding you that whenever you're finding an angle measure using trigonometry, you'll end up needing to use at some point in the problem an inverse trig function in order to get an output of an angle. The input is a ratio, the output from an inverse trig function is an angle measure. So let's just go ahead and go for it. That the law of sines in this case would say first start with the angle side pair that you're given and set up that in a ratio. That the sine of 69 degrees divided by 250 is equal to, let's choose b in this case because we're given the opposite side b. The sine of angle b divided by 150. From there, notice that the missing value in this case is an angle measure, so we'll end up needing to use an inverse sine. Cross multiply first. 150 sine of 69 is equal to 250 sine of angle B. Divide both sides by 250, and you get sine of B is equal to 150 sine 69 degrees divided by 250. And then from there, I have a ratio, and I'm solving for the angle. So if I want to solve for the angle, I use the inverse trig function, that the measure of angle B then is the sine inverse, or the arc sine, it's sometimes called, of, no, don't type stuff. The arc sine, or the inverse sine of sine 69 divided by 250. And I know that looks funky, but that's the exact thing that you're going to stick into your calculator, that you'll first select the inverse sine option. Then on the inside of those parentheses, you enter 150 times sine of 69 and divided by 250. And from there, I get that the measure of angle B is approximately 34.1 degrees. And just keeping in mind that we round angles to the nearest tenth, 34.1. Now, since I have two angle measures in this case, 34.1 degrees, I can use the triangle angle sum theorem to find out what the other measure of the angle is by taking 180, subtracting 69, and subtracting 34.1. And I get that the measure of angle C is 76.9 degrees. 76.9. Then from there, finding the value of length C is much like we did in the other problem, because since we're finding a side length, we're not going to end up needing to use an inverse sine. But use one of the angle side pairs that we have. I'm going to stick with the one that we've established from the get-go, that the sine of 69 degrees divided by 250 is equal to the sine of 76.9 degrees divided by its opposite side length C. Cross multiplying, I get that C sine of 69 is equal to 250 sine of 76.9 degrees. And then lastly, divide both sides by the sine of 69. That C is 250 sine of 76.9 degrees divided by sine of 69 degrees. And if I enter that into my calculator, 250 times sine of 76.9 divided by the the sine of 69, I get 260.817 centimeters. Really, those are the only examples you might see of the law of sines and the law of cosines. The only difference is that I might not give you all of the information in a diagram. It would just be your goal to sketch the triangle yourself. That might be the goal in this situation. But once you've sketched the triangle, use your angle side pair to set up the law of sines and solve for either the missing angles or the missing sides. While I will include